Hi, hello and welcome to Chat Physics Live 2022. I'm Alexia. I'm going to be talking to you today about particle physics, which if you know me on Twitter isn't that much of a surprise. You might know me by Miss Neutrino. Now, my title is Introduction to Particle Physics for an Enthusiastic Physics Teacher. If you're concerned you're not enthusiastic enough, maybe consider that you're watching this video and realize, yes, you are definitely enthusiastic enough. So today I'm going to be basically doing a quick introduction to the fundamentals of particle physics. I'm going to share with you some of my favorite stories, and I'm also going to share some resources that I found very useful when teaching particle physics. I'm not going to be giving a comprehensive introduction to particle physics. We just don't have time for that. And it's definitely not going to be enough to prepare you to teach particle physics, but hopefully it should give you some more depth and give you a bit more of a science background that's not purely focusing on textbook information. And as such, this is not exam board specific. And what I'm talking about and the answers and the information I'm giving you is not primed for exam answers. This is very much focused on increasing your subject knowledge to enrich your lessons and your teaching. So let's get started. What is particle physics? Well, particle physics is a study of some of the most fundamental stuff in the universe. It's the most fundamental particles. We don't go any smaller than that. And these particles make up something called the standard model of particle physics, which describes these particles in their interactions with each other. Now, something I feel like is important to point out is we are adapting and growing our definition of what a particle is. Probably so far, students have thought of particles as sort of, little solid bits of matter. And maybe that's always been a little bit wrong, but it's now even more wrong. Because now when we think of particles in this context, we're sort of thinking of points in space that don't necessarily have dimension. They're not necessarily made of matter or even mass. We have matter particles, which make up matter, but we also have force particles, and some of those force particles have a mass of 0. So particle now means something slightly different. And we also have composite particles in particle physics. So these are particles which are made up of those fundamental elementary particles, and this is things like protons and neutrons and other hadrons. So why is it important to study particle physics? Well, it's a really fundamental thing about the universe. It's really trying to work out what the universe is made of on the most fundamental level. And because of this, it's a very big area of cutting edge research. There's still so many questions being answered. Even if you're not that interested in particle physics itself, it also links in with so many other topics. So it's really important for students to have a bit of a grasp of it, because then when approaching other topics, they have that background knowledge. And finally, it's fun and cool. It's a bit weird and wacky. It's not quite as straightforward is maybe the wrong word, but it's not the world necessarily they see around them. It's a slightly different world. And I always, as a student, found that very interesting and very cool. And hopefully your students will too. So on to the standard model. So as I said, this is the model that underpins particle physics. It describes the particles themselves and also their interactions with each other. In physics, you sometimes see this as a very big equation called the standard model Lagrangian, which is a big equation which describes those interactions of the particles. But here we're going to look at this graphic version. So it is an incredibly successful model. It's made lots of predictions which we've found out to be true. So such as the Higgs boson. So the Higgs boson was predicted by the standard model and then found. So the Higgs boson is the particle that gives other particles mass. However, while it is an incredibly successful model, it doesn't quite have all the answers. So for instance, the standard model says neutrinos should not have mass, but they do. So that is an area that we're really looking into, and we're trying to work out what the answer is there. So it's a great model, we love it, predicted a lot, but there's still enough gaps for there to be a lot of active research going on. Now, to look at it in a bit more detail, these first 3 columns coming in from the left, these are our matter particles. or fermions, named after Fermi, and we've got the ones at the top, which we call quarks, and the ones at the bottom, which we call leptons. Now this first column, which has that Roman numeral 1 above it, so that's what we call our first generation. We have the up and the down quarks. So these make up protons and neutrons. So proton is 2 ups and a down, neutrons is 2 downs and an up. And then we have the electron, probably the best known particle in the standard model. And we've got the electron neutrino, which is produced as part of beta decay and is the neutrino partner to the electron. If we go to the next column, which has the Roman numeral for 2 above it, this is our second generation. Really handy. Second generation acts just like the first generation, but everything is heavier. So charm, heavy up, estrange is a heavy down, a muon is a heavy electron, a muon neutrino is a heavy electron neutrino. And it's the same for the third generation, all the same qualities, just heavier. But because those particles are heavier, they are more rare because they require more energy to be produced, and then they decay more quickly. They're more unstable due to their higher mass. And this means we don't see them around as much. And so that's why the world around us is made up of this first generation primarily. Now, those are our matter particles. So we know the up and down. So those make up protons and neutrons and atoms. And then in that fourth column, we have some of our bosons. So bosons named after Bose, these are our force carriers. So the one that we're probably most familiar with, the photon, is the force carrier for the electromagnetic force. And so we're looking now as forces, we're not looking at fields, we're looking at individual force carrier particles interacting in order to have interactions of that force. So for instance, an electron scattering electromagnetically, you would see a photon being exchanged. So the photon is electromagnetic force, and so it interacts with all particles that have electromagnetic charge. We've got the gluon. So the gluon is the force carrier for the strong force, and the gluon acts on the quarks and it sticks them together to create composite particles like protons and neutrons, and it only acts on the quarks. And then finally, we've got the Z boson and the W boson. These are the force carriers for the weak force, and they interact with all of the matter particles. But we don't see that many weak interactions, and that's basically because the weak force bosons are incredibly heavy, and so we just don't see them around as much. If we were in a high energy environment, we'd see a lot more weak interactions. And finally, we've got the Higgs boson, which is a bit different than the other bosons, and it gives all of the particles with mass their mass. Now, a quick thing I want to just mention about the gluon and the strong force is when teaching sixth form, we often talk about the nuclear force or sometimes a strong residual force. This is basically the leftover bit of the strong force. So the strong force glues the quarks together, and then the leftover force you've got helps glue the protons and neutrons together in the nucleus. So the protons and neutrons are not glued together directly by the strong force, but by kind of the leftover bit, sometimes the residual strong force, or also known as the nuclear force. So that's our quick introduction to the main bits of particle physics. And I'm now going to tell you about some of my favorite stories that I really find very useful in enriching teaching this topic and giving a bit more context. So the first story is about the naming of the quark. And I really like this story because I think it really shows that physicists are not as one-dimensional as a lot of students think. Physicists can be interested in literature, they can be interested in music, and literature specifically is the story here. So the quarks were named by Gell-Mann, who was one of the first people to put forward the quark model. He was one of 2 people to put it forward. And when he was trying to think of a name, he came across this line in a book by James Joyce. It's a book called Finnegan's Wake. And the line is 3 quarks for Mr. Marks. He thought it worked quite nicely. We know that in a proton and a neutron, there are 3 quarks, so why not call it a quark? This story is also very good if any students ask about how do we pronounce quark? So personally, I look at this line, I say 3 quarks for Mr. Marks. Quark must rhyme with Mark. But Gell-Mann, even though he chose this quote, seemed to want to be difficult, in my opinion. He thought, within the context here, quark is meant to mean quart, as in 3 quarts of liquid. And so we should be pronouncing quark as quark. So there are arguments for either side. I personally like to go quarks rhyme with marks, but you could put it to your students, see what they prefer. Both versions are used within particle physics. My second favorite story is also a quote, but not one from literature this time. It's one from a scientist, and it's from a scientist on reacting to realizing what a muon is. So when the muon was first observed, we didn't really know what it was. We saw it was heavy and we saw it had negative charge. And we assumed that it must be similar to protons and neutrons. But we started to notice it didn't quite act like that. So the forces we were expecting it to interact with was the nuclear force. So we're expecting it to interact with protons and neutrons in the same way protons and neutrons interact with each other. But we just covered that protons and neutrons, that nuclear force is actually the leftover bit of the strong force. And the strong force only interacts with quarks. So the muon, which is just a heavy electron, it's not a quark. It's not going to interact via the strong nuclear force. And when we realized this, and when we realized it was just a heavy electron, that didn't really make sense with our model at the time. And so Rabi, who was the Nobel laureate who won his Nobel for nuclear magnetic resonance, basically just said, who ordered that? It was an occasion of not expecting something and finding something. And then we have to then build a model that works around that. And talking about building models, that brings me to my last and favorite story, which is the proposal of the neutrino. And this is linked to, you can see in the slide, a picture of a letter. Now, this letter was written by Pauli to a conference he wasn't able to attend. And he opens the letter brilliantly saying, "Dear radioactive ladies and gentlemen." Now, Pauli is concerned. He is concerned about the problem with beta decay. What's the problem with beta decay? Well, the problem with beta decay is we have sort of, a start and an end state. We have something turning into something else and emitting an electron. Now we've got the same thing happening each time, okay? We've got the same transformation. So it should be the same energy emitted each time. We've got energy conservation. If you've got all the same things happening, you should get the same outcome each time. You can't just magically lose energy to something, right? Except that was what was happening. We were observing the electron and it was having this big range of energies and it didn't make sense. And Pauli basically, he proposed the idea of a neutral particle, which he called a neutron, which was carrying away the energy. Now, this particle ended up being called the neutrino and is the neutrino that we know and love today. And I love this letter as a little bit of history. It opens beautifully and it's only about 2 or 3 paragraphs long. I think you can see actually 3 paragraphs at least here. And so it makes it brilliant as a little piece of comprehension. And he really talks through his thinking of, okay, well, what's the problem? How do we fix this problem? What qualities must the particle that we propose to fix this problem, what qualities must it have? And so it's a really great little example of how physicists solve problems. Okay, my last and final thing is just covering a few resources. So I will say none of these resources are textbooks. I wanted to give you resources which are a bit more focused on broadening your subject knowledge, although some of the resources do link into pedagogy and teaching. So the first one, Lego particle physics. I love using Lego to help teach particle physics. It's fun. And it gives a visual to something that's otherwise quite abstract. So Dr. Ben Still is kind of like the king of Lego particle physics, and he has this brilliant book. And he also worked with Queen Mary's previously and put together Lego particle physics with them. And that is also a series of PowerPoints and lesson plans, so that can be really useful. Dr. Ben Still has also put together some videos, all of which are really great for teaching the basics. And also his book is brilliant. I highly recommend getting a copy of it for your library or for your classroom. Hyperphysics is my next recommendation. If you've gone to university and studied physics in the last decade or so, or even longer, you probably know of hyperphysics, but I wanted to highlight it in case you didn't. It's basically like Wikipedia for undergraduate physics, but shorter, clearer explanations, not as much fluff. It's really great if you just want to like boost your knowledge on a topic a little bit before you teach it, so you can be prepared for those tricky questions. And the final thing, the final big one thing I want to share is the Particle Data Group Review of Particle Physics. This is the holy grail of particle physics. It has all of the information that you could ever want. Because of this, it is a little bit dense and detailed, so you don't really want to sit down and read it in the evening. But if a student has a question like, you know, how many different decays are there for a tau particle, or, you know, what's the lifetime of a top quark, just that kind of, those kind of questions, all of that will be here. So it's really great. So that we've got some other good resources here. Symmetry Online magazine is my favorite online magazine that is only particle physics. So you can go there, everything's particle physics. Frank Close has some amazing books that I really love. He's got Neutrino, is my favorite one, but he's also got a short introduction to particle physics. Those are really good, I think, for you to boost your own subject knowledge. The chapter on particle physics by Ravelli in his 7 brief lessons is beautiful, and I've used it as comprehension work or as an introductory thing for students to read as homework before starting particle physics. It's not overly long, so just gives you a brief snapshot. And finally, if you want something that's going to tie in particle physics and nuclear physics and the more general ideas of how students see particles, the particle chapter by Ben Rogers in his Big Ideas in Physics and How to Teach Them, really nice. I highly recommend the few paragraphs on Rutherford's gold foil experiment, very good. So that is my quick introduction to particle physics. It is very quick, so if you do have questions or if you want to probe my brain for information on particle physics, please do reach out to me on Twitter and Instagram at Miss Neutrino, and I really hope you enjoy the rest of Chat Physics Live 2022. I know I'm going to be watching many of the videos. Thank you very much for listening.